Oh, all right. Well, welcome everyone to this evening's webinar presented by Mohonk Preserve. I want to thank you for attending one of these. We have a lot of virtual programming that is on our website. And we have a virtual recording page, and it has lots of archived presentations, and this one will be included in that. I can send that link out to everyone afterwards. This evening's topic is called Playing in the Mud, which I just love that. Playing in the Mud, how Earth scientists learn about climate change. And our presenter this evening is Dr. Kirsten Menking from Vassar. And my name's Lauren Bohr, and I'm an education coordinator here at Mohonk Preserve. I do the public and youth programs for the preserve. I'll be monitoring this program and checking out the chat. And if you do have any questions, feel free to put them in the chat. If something pops up in your head right in the middle of the presentation, please use the chat. We'll have enough time at the end for questions. So we'll kind of have a Q&A time at the end there. And as always, I think we've gotten very used to doing a lot of these. Everyone, I think, is familiar with keeping yourself muted just so that there's no distractions during our presentation. And yeah, so we'll have enough time for lots of questions at the end. And I know I'm very excited about this. A passion of mine is earth science and learning about climate change and teaching others about climate change. And Mohonk Preserve has a long history of keeping phenology and climate data. It goes all the way back to the 1800s. And we were actually just discussing the Tempestry project through Vassar, and that is showing the temperatures over the years, the average temperatures over the years through knitting, which, craftiness, using art and science together. It's a wonderful project. So if you can learn more about that, and maybe even Dr. Menken can talk maybe a little more about that if people have questions. So I love it. So let me introduce our presenter this evening. Dr. Menking earned a bachelor's degree in geology from Occidental College in 1990 and a PhD in earth science from the University of California, Santa Cruz in 1995. And she has been on faculty at Vassar since 1997, where she teaches courses in earth science and geography and the environmental studies interdisciplinary program as well. So I know that we're just saying like how long you've been at Vassar. It's hard to believe how many years you've been there. And I am, like I said, I'm excited to hear your presentation and learn more about playing in the mud this evening. So without further ado, here's Dr. Menking.
All right, great. Thank you so much, Lauren. And I'm going to try to share my screen here and see if this works. Can everybody see my first slide?
It looks good. I can see it.
All right, excellent. All right, so playing in the mud. So this talk, I've given it many, many times, and it's actually kind of an old talk because it deals with a paper that I published back in 2012. But the reason why I'm giving it is because it's very specific to Mohonk, because it has samples from Lakes Mohonk and Minnewaska. And so I think it's appropriate to talk about it in this context. So this figure here, my title slide, shows how the temperature of the Earth has changed over geologic time, all the way back from the very beginning of geologic time, the Archean here, about 4.5 billion years ago or so, up to the present day. And you'll notice that the scale on the y-axis here is not linear. So there's a lot of time represented by this early part, and then very little time represented by the more recent part of the figure. And the other thing you'll notice is that the temperature has changed quite a bit over geologic time. There have been times when the Earth has been hotter than today and times when the Earth has been colder than today. The way that we figure this out is by looking for clues in the landscape and in the rocks that tell us what the climate was like in the past. And so that's what this talk is about. Another thing I want to point out is that there seem to be a lot more squiggles up here. Can you all see my cursor? Can you, when I wave it around?
I can see your cursor. Yep.
Okay, good. All right, so you see a lot more squiggles up here. That's not because the climate has been fluctuating more in the present day. It's simply a matter of the fact that we have more evidence in the more recent rock record because erosion and things like plate tectonics, mountain building events have erased some of the fine scale variability that as we go back farther in time. So no doubt climate was gyrating wildly throughout this entire 4.5 billion year time period, but we just don't have as much evidence as we go farther back in time. So, oops, how am I going to advance my slides here? It's not letting me. Okay, here we go. All right, so if we were to go back to Earth 20,000 years ago, this is what it would have looked like. And notice that there's a giant continental size ice sheet, kind of like Antarctica, sitting on top of North America and coming all the way down into New York. In fact, the island of Long Island is made up of sediments that were deposited out in front of this big ice sheet. And so the gunks were completely submerged in ice or covered in ice. And the evidence of the ice sheet's existence comes from a lot of different landforms that are left behind as the ice retreats. So we have these ridges of sediment that were pushed out in front of the ice called moraines. And then we've got material underneath the ice sheet that's kind of made up of a mixture of big rocks and clay-sized particles that were produced when the big rocks were dragged over the underlying bedrock and basically grinding up the underlying bedrock like sandpaper would wear away wood. And you know, anybody who has tried to have a garden in this part of the world knows how difficult it is because you put your shovel in the ground and you you hit a rock. So that's all ground moraine material. And then, you know, as the ice continues to retreat, you start out with this completely barren landscape that then gradually changes over time as plants move into the environment. And this figure is just showing where the ice was at different times in the more recent past. So each one of these numbers on here is a number in thousands of years. So this little number is 18.8 thousand years ago. The ice was in this area. And then about 18.3 thousand years ago or so, the ice was in this area. And the gunks are sitting in here, somewhere around in here. And so the ice moved away from this area somewhere between 17, 18,000 years ago. And as it did so, you know, the landscape experienced profound changes. And this figure shows what's happening today in a place like Glacier National Park, where a warming climate is causing the glaciers to retreat. And notice that as the ice disappears and backs up, we get these lakes forming in the landscape. And that's significant because lakes are really wonderful recorders of everything that's going on in the watershed. And they allow us then to decipher the climate history of an area based on biological, chemical, geological clues that we find in lake sediments. So if you think about the fact that every fall, the trees in this area drop their leaves, all of that organic material is going to wind up falling into lakes or being blown into lakes. every spring, the trees are pollinating and the pollen's blowing around, and some portion of that is going to wind up falling into the lake. If there's a forest fire and the trees burn, charcoal that's in the air is going to get blown into the lake, or washed off of the hillsides into the lake. And because sediments accumulate over time, we get a temporal record of what's going on in this watershed over time. So you could imagine like what would happen if suddenly the climate in New York became arid. Well, the trees that are presently here wouldn't be able to survive any longer because they require more water, and maybe cacti would move into the environment. And so we would get a totally different type of pollen blowing into the lake, and we would get totally different plant macrofossils coming into the lake. And we don't see anything that extreme, but we definitely see variations in vegetation over time that allow us to reconstruct changes in temperature and precipitation. So a lot of the work that I've done has been on counting pollen grains. And here are some examples of different pollen types that are found in Hudson Valley lake sediments. And what's nice about pollen is that it's pretty easy to learn how to identify, and the different genera of pollen have very distinctive shapes and sizes. One thing that is difficult with pollen is getting below the genus level to the species level. And for most things, you can't do that. But we still know, for example, that hemlock trees tend to like conditions that are generally wetter than oaks in this type of environment. Birch trees like things colder than oak trees do. And so a lot of the information that we get is rather qualitative, but still can help us understand what was going on in this environment over time. So just in terms of where we are, here's Vassar, here's the ridge, and we'll look at Minnewaska and Mohonk. So I've taken lake sediment cores from both of these lakes, from Minnewaska first, and then later from Mohonk. And one thing that's interesting about these lakes is, well, first of all, they're considered to be glacially plucked. So they were holes that were created by the ice pulling away bedrock and carting it off to the south. And the lakes don't have inflow streams really to speak of much. And they have fairly small drainage areas. So whatever is going on locally is going to be recorded, and we don't have an influence from someplace far away that we have to worry about. So it's just the local environment that they're sampling. And oh, sorry, this is I forgot I had this slide in here because I spoke to the freshmen earlier this year about about what was going on here, and I was trying to convince the students that they should take some earth science classes. I should have taken that out for tonight. All right, so here's Lake Minnewaska, spectacular jewel of a lake, and Mohonk, of course. And we don't take sediments from the bottom of the lake, or I don't generally, from a boat, because I find it very difficult to do that. So my preference is to wait until winter time comes and to go out on the frozen lake surface and then cut a hole in the ice. And we then take some PVC drain pipe, which you can see here in the background, and we create a column of PVC going all the way down to the sediment water interface at the bottom of the lake. And the purpose of that pipe is to guide the corer, which is this tube right here, into the same hole over and over again. And this is just a hollow tube of metal, and you thread onto it these rods that are sitting over here on the snow, until you get all the way down to the bottom of the lake, and then you push in to the mud a meter, and you pull all of it back out of the hole again, extract that meter of mud from the core tube, and then put it back down and push the next meter in. And we then bring that mud back up to the surface, in each time. And as we push it out, we put it into a PVC pipe tray, for transport back to the lab. And I should mention that we do this work usually sometime in February. The ideal conditions are when the temperature of the air has been in the low 20s for long enough that we get at least 6 to 8 inches of ice on the lake surface. And then we want the air to be cold enough that the lake remains frozen so we don't fall through, but not so cold that the core freezes while we're doing it. So 28 to 29 degrees Fahrenheit is probably about the ideal temperature for coring. And all of these rods fill up with water as we are dropping the core down there, and then they have to be unscrewed again. And so there's water pouring all over the place, and it's 28 degrees outside. And so it's not for the faint of heart to do this kind of work, because you end up getting, somewhat wet and it's freezing. So, but, and in this case, in Minnewaska's case, we went down, I believe it was about 70 or 80 feet to get to the bottom of the lake. And where we cored at Mohonk, it was more about 30 to 40 feet where we went down. So here are some pictures of my students helping with this process. And here's Dorothy Petit, who has been a collaborator on this work and on some of the other lakes that I've been working on here in the Hudson Valley. And here you can see where we've shoved the mud out into the waiting PVC tray. And this is what the mud looks like. So here is the first about meter of Lake Minnewaska sediments that we took, and it's pretty nondescript. You look at it and you go, it's black, kind of gelatinous muck that doesn't really look like much of anything. But as you go farther down in the sediments, you see that there's a change. So here's 101 to 150 centimeters below the sediment water interface, and we see that there's this transition right in here from the black muck to what looks like a gray clay. And then going farther down, there's more gray clay. And then underneath the gray clay, there is sand, and the sand is, in some cases, very strongly layered. And so just looking at the sediments themselves, I can immediately tell a couple of things. The first thing is that in order for there to be sand in the lake, there's got to be water flowing into the lake, because you need a current to transport large sand-sized particles. And so that's an indication that the ice has just left the area, but there's still some ice up on the ridge, and there's meltwater that is bringing sediment into the lake. But then notice how there's this abrupt transition where the sand stops and it just becomes clay. And I think that at this point, there's no longer any ice on top of the ridge. And because there's no longer a bunch of water pouring into Lake Minnewaska in a stream kind of setting, we're just dependent on the wind blowing fine-grained sediment or very small trickles of water bringing this clay-sized material into the lake and settling. And then here, the landscape stops being completely barren of plants and the forest arrives. And the sediment completely changes character from being sedimentary particles that are made up of ground up rock to now being black gelatinous muck that we call gytja, which is a Norwegian term that means black gelatinous muck, and it's entirely organic in makeup, or mostly organic in makeup. So the other thing that we do, though, is we process these sediments for pollen and for plant macrofossils. And the pollen processing is rather intense. It requires treating the samples with very, very strong acids that the pollen doesn't care about at all, but everything else goes away. So we have to get dressed up in a lot of safety gear because some of the acids we're working with will eat right through a body if they get spilled on you. And we put in hydrofluoric acid and it dissolves away all the sand grains that are in there. And we put in something called potassium hydroxide, which will get rid of a lot of the organic matter. Sometimes we also use acetic acid and then sulfuric acid to further get rid of organic matter if there's a lot in there. But remarkably, the pollen is not bothered by any of these chemical treatments at all. It's almost like it's made out of plastic and it just really doesn't care. So after we dissolve everything else away, we're left with these pollen grains that we can then put on a microscope slide and look at. And we then identify the different pollens that are present and we count how many of them there are. And we create these pollen diagrams like you see right here. And this figure on the left-hand side is just a schematic drawing of what those Lake Minnewaska sediments looked like. So you can see the sand here at the bottom and then the gray clay on top of that. And then we go into this kind of transitional zone where the forest is arriving and things are becoming more organic rich going up the core. And here's a figure right next to that shows the organic carbon content of the sediments, and you can see there's basically nothing until we get to that transition zone, and then suddenly the organic carbon content spikes up. So here's the arrival of the forest in the environment. And when did that happen? Well, somewhere around probably 16 to 17,000 years ago. We've got two different timescales here, and I'll talk about how we date these things in a moment. But I want to point you to what the pollen is showing. So we don't bother to look for pollen in these sediments down here where there are no plants in the environment. For one thing, you can probably find a pollen grain or two, but they're so few and far between that it would take you weeks and weeks to find enough of them to count the 300 or so that we count for statistical significance. What we see though at the base of the organic rich interval is that there's a lot of spruce and fir trees and a lot of pine. So what does that mean? Well, let's think about what spruce likes in terms of its conditions. Here's a white spruce. There are black spruces, blue spruces, whatever, but white spruce is a common species today in Canada in the Adirondacks. And what we're seeing is that there's a lot of spruce pollen way down here in southern New York. And this figure on the right-hand side over here shows where spruce is present and where it is absent based on the range, the annual temperature range that it can tolerate, the annual average temperature, the January average temperature, and the July average temperature. And the bottom line in each one of these cases is actually showing all temperature space for North America. So in January, for all of North America, from Panama all the way up to, you know, the extreme northern parts of Canada, the temperature range is somewhere between 30 degrees Celsius and minus 35 to 40 degrees Celsius. And spruce will live in places where the January temperature is between about minus 32 and about minus 5 or so degrees Celsius. And for July's temperature space, it can not inhabit anything warmer than about 20 degrees Celsius. All right, so what is that? Well, that's getting up into the upper 50s Fahrenheit or so. And so it doesn't like the warm conditions that we have here in the Hudson Valley in the summertime today. And that's why we don't find it here today. We find it farther to the north. So what did our area look like back at the time that the forest first appeared? Well, it probably looked kind of like boreal forest today that we see in places like the Adirondacks and Canada, and looked, you know, this is what was roaming the landscape at that time, right? We had mastodons, we had woolly mammoths running around in this kind of environment. So if we now go a little farther toward the present, what we see is that the spruce and the fir disappear, and instead hemlock starts to rise, and so does the oak. The oak was present before, but it undergoes a major expansion at this point. And let's think about what that means. All right, here's hemlock. You see these trees around here all the time. They're suffering right now from an invasive pest insect called the hemlock woolly adelgid that's been killing them off. But these trees have been around for quite some time. But if we look at the temperatures that they like, what we see is they can't tolerate conditions nearly as cold as the spruce. Remember, the spruce went all the way down to about minus 35 or so in its temperature tolerance in January. And they can tolerate warmer temperatures in July than the spruce could. And so the fact that the spruce disappears and is replaced by something like hemlock is an indication that the whole climate is warming. So people have done this kind of work by looking at vegetation records from all over the Northeast, and they have revealed how climate has changed over time as that big ice sheet retreated. And these are different time slices. So this is 18,000 years ago, 12,000 years ago, 6,000 years ago, and today. And you see that 18,000 years ago, we had a tremendous amount of ice on the landscape, and 12,000 years ago, still quite a bit. And by 6,000 years ago, it's basically gone. And we see that the spruce pollen was going all the way down into northern Mississippi, Alabama, Louisiana area. And then as conditions got warmer, as the ice retreated, the spruce migrated northward in search of of colder climates. The one other thing I wanted to point out on this slide here is that Florida looks incredibly odd 18,000 years ago, and that is real. That's because in order to make all of this ice on the landscape here, you got to pull the water from somewhere, and it comes out of the oceans, right? It evaporates, and then it's precipitated on land as snow and eventually builds up into these big ice sheets. And that means that the sea level dropped, and that's what made Florida so much fatter 18,000 years ago than it is today. And I'll leave you to ponder what it means for Florida if the Greenland ice sheet melts because of human-caused global warming. All right, so now what I want to do is talk to you a little bit about how we figure out when different events occurred. So I've just, talked about how we can see the temperature changing from cold to warm with the departure of the spruce and the arrival of the hemlock. And how do we know when that happened? And so we need to do a little digression here into radiocarbon dating, which is what we use to figure out the timing on things. And the basic idea behind radiocarbon dating is that in the atmosphere, cosmic rays, neutrons are constantly coming in from outer space, and they are bombarding nitrogen atoms and turning them into a form of carbon. So what happens is that a neutron comes in and a proton from the nucleus of the atom gets ejected. And what makes an element be a particular element is how many protons it has. So nitrogen has 7 protons and 7 neutrons. And if a neutron comes in and a proton gets kicked out, then suddenly we have a different element because the atomic number, or the number of protons, goes from 7 to 6. And so this is happening in the atmosphere all the time. But this particular form of carbon that's produced, it immediately reacts with oxygen in the atmosphere and makes carbon dioxide. And that carbon dioxide is then taken up by plants in photosynthesis. And then the animals come along and they eat the plants. And this particular form of carbon happens to be radioactive. What does that mean? Well, it means that the carbon will turn around and turn back into nitrogen at some fixed rate. And so we've got different types of carbon in the atmosphere. There's this radiocarbon, this carbon-14, that's being produced by these processes. But there's also non-radioactive carbon, carbon-12, and there's also a carbon-13. And they're all carbon, meaning they all have 6 protons, but they have differing numbers of neutrons. So carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. And so the plants are taking up all these different forms of carbon, and the animals are always eating the plants. And so we are slightly radioactive, all of us, and all the plants out there in the world are slightly radioactive because we have this radiocarbon in our tissues. And as long as we are eating, or as long as the plants are photosynthesizing, so in other words, as long as things are alive, the radiocarbon that's being ingested is constantly replacing the radiocarbon that's breaking down in our tissues and turning back into nitrogen. And at the minute that we die, that process stops. So the carbon-14 is decaying back to back to nitrogen-14 at a known rate. And so when plants and animals die, the ratio of the carbon-14 to the carbon-12 in the organic matter that's left behind in the tissues of the dead animal or plant will start changing. All right, because the carbon-14 starts to decay away, but the carbon-12 stays fixed. And the amount of time that it takes for the carbon to turn into nitrogen is known as the half-life of the carbon. And that happens to be about 5,370 years for radiocarbon. So let's say you had 100% radioactive carbon in a pine cone, then in 5,370 years, only 50% of that radiocarbon would remain, and the rest of it would have turned into nitrogen. And after the second half-life, so 10,740 years ago, if I'm doing my math in my head right, then we would have a quarter of the radiocarbon remaining, and the rest would have turned into nitrogen, and so on. And so we can measure the amount of radiocarbon that is present in some organic matter using an instrument called an accelerator mass spectrometer. So if we can find like a little birch seed or something in our lake sediments, we send that off for dating, and the lab burns the seed and turns it into carbon dioxide, and then the carbon dioxide goes flying down a flight tube that's curved, and the carbon-14 has a heavier mass or weight than the carbon-12 does. And so as the carbon dioxide goes flying down the flight tube, the two strands of carbon, the two types of carbon, diverge because they have different momentums because of their different weights. And they sling into different detectors. And so we can tell how much C14 is present in the sample relative to C12. And that's then an indication to us of how many half-lives have gone by since this thing died, whether it's an animal or a plant. And so that's how we get the ages of things. There's a little bit of technicality in converting the radiocarbon dates to actual calendar dates that I don't really want to get into right now. If people want to ask me about that, I can later on talk about that. So what we see over here on the left-hand side then are different intervals where we picked out some kind of plant macrofossil, like a little piece of pine needle or a little hemlock needle or a little spruce cone or a birch seed or something, and we sent that off to the lab for dating, and then here's the date next to it in both in radiocarbon years and then in calendar years that's been converted. And what I want to do now is look at some of the record from Mohonk Lake, and here, instead of looking at pollen, we're going to look at the presence of different types of plant fossils within the sediments. And there's this interval that's really interesting in the Mohonk record, right in the middle here. If we look at the Mohonk record, we see a lot of similarities with Minnewaska in that there's some sand at the bottom and then there's some gray clay. But then there's some different layering in here where Minnewaska just had basically organic matter going up to the top. Here at Mohonk, we've got this interesting sand layer right here in the middle of the record. And this sand layer happens to coincide with a time when we have an elevated amount of pitch pine needles, and we have an elevated amount of charcoal in the samples. And we also have some other things that are aquatic plants that only appear in shallow lake settings. And this seems to be an indication of a drought period. And the reason why I say that is because pitch pine is a fire adapted pine. And so it appears that the landscape here has dried out and is burning from time to time. And what we know about forest fires is that they tend to burn off all of the understory vegetation and the leaf litter that would otherwise hold the soil in place and protect it from erosion by rainfall. And so we would end up then getting a lot more soil erosion that would allow for the sand layer in the lake. And we also have all that charcoal that's coming in from the burned trees. So it looks like we had a big drought in the middle of that that time period there. And if we look at the pollen record, what we see is that the hemlock pollen, which had been quite robust in that time period here, beginning around 10,000 years ago, it suddenly drops off dramatically. And if we think about hemlock again, we looked at what hemlock meant in terms of temperature, but let's think about what hemlock means in terms of precipitation. Oh, sorry, before I get to that, here, if we look at Lake Minnewaska, here, what we see is that the top of the Minnewaska core is about 4,800 to 5,000 years ago, which is the same time as the sand layer is happening in the Mohonk Lake record. I can explain later why we don't have more sediment at the top of Minnewaska. We lost a bunch of the record here. So this is basically the same time that Mohonk has that sand layer that's got all the pitch pine and where the pollen shows the hemlock decline. And what we see is that at Minnewaska, there's just a huge number of hemlock macrofossils in the record at this time that indicate that the hemlock forest is dying, and it's just all the trees are just shedding debris into the lake. And so thinking now about what hemlock likes in terms of moisture, it has a really pretty high moisture requirement on an annual basis of, at least a meter of rain or so at least a yard of rain. And so the fact that we see this collapse in conjunction with the high charcoal and the pitch pine suggests that we're talking about a very, very long drought that killed hemlock by creating a lower rainfall rate than we see in the present day. And in fact, the radiocarbon dating suggests that the drought was probably about 1,800 years long in the middle Holocene. So here's the summary of conditions that we were able to put together by looking at these two lakes together. And we see that conditions were originally kind of cool and humid, and then became colder and wetter, and then back to cool and dry, and then cold and wet again, and then warm and dry, and warm and wet, and then warm and dry. And this is that drought interval that we see in the hemlock information, and the charcoal and the increased sediment to the lake. So what are the implications for us here in the Hudson Valley? And more importantly, what are the implications for New York City's water supply system? So the gunks are sitting in here in between the two giant watershed water supply systems for New York, the Catskill Delaware system that has all these reservoirs that feed drinking water to New York City, and then the Croton watershed here. And so if something like this kind of a drought were to recur again, New York would be in a real world of hurt because they're presently getting something like 10 billion gallons a day of water, from these two sets of watersheds. And so it's important for us to be able to reconstruct the climate history of an area because it allows us then to understand what could happen in the future. And it's also important for us to think about how is future warming going to, affect the water supplies of this area. At present, the Mohonk data indicate that New York is getting wetter and wetter over time. Over the last century or so, it's gotten wetter with global warming. But whether or not the warming will lead to increased evaporation to the point where the evaporation starts to outweigh the increased wetness remains to be seen. So I'm just going to end there, and I'm happy to entertain any questions that you might have about any of this.
Yeah, I was taking notes. This was a really great presentation. And actually I was coming up with questions as you were talking, but then you answered them. So that was wonderful, your presentation. But yeah, I'm
Okay,
happy to
good.
open up to any other questions. It looks like maybe Paul, if you have a question, you can go ahead.
Sure, a fascinating work you're doing. I'm doing some cave research up in the Clarksville area, looking at
Uh-huh.
sediments were in a glacial lake within a cave. It
Okay.
includes a layer of charcoal that's greater than 43,500 years old by radiocarbon dating. But I'm curious if not only do we preserve the charcoal, but if there might be pollen in all the finely stratified layers that we could look at the climates at least back into the Sangamonian and Illinoisan.
Yeah. I mean, there should be pollen. So my late partner actually did a pollen study across the Cretaceous Tertiary boundary in rocks, and he pulled it out of rocks.
Good.
So you can get it out of anything, as long as you've got plants that were there. And so we definitely should be able to look at those lake sediments and find pollen in them. Now, the question would be, what are the sediments? Are they largely clastic? I take it you're a geologist.
Yes.
Are they
Uh,
clastic or are they organic?
Primarily clastic. We have clays, sand, silts, and debris flows, a mix, finely stratified
Uh-huh.
deposits.
Yeah. So there the issue is going to be kind of the same issue that I had with looking at trying to find pollen grains amidst all of that clastic debris can be hard because it's so diluted with all of that stuff. But it doesn't hurt to look. You could treat some samples and see what they show, but you might need a fairly large sample volume to get the pollen to a high enough concentration to be able to see it in the sediments. And usually what people if people are interested in looking at the clays, they'll find things like sedge pollen in there from just when the ice retreated. But I don't have the patience to wade through
Right.
slide after slide after slide, trying to find, one pollen grain on each slide. So I tend not to bother, but can always look for stuff.
Great. Thank you.
Sure. Where are you located, Paul?
Well, the cave's in Clarksville. I'm over in Tivoli, not far away.
Uh-huh.
So up in the Albany area.
Okay. I don't
Perhaps
know where Clarksville is.
it's about 20 miles west of Albany.
Okay. Cool.
Yeah, perhaps you'd like a new research project.
You know, when I first came to Vassar, I was trying to get in with the caving community because I thought it would be fun to try to find some stalactites to look at. But I just found that everybody I talked to shuttled me to somebody else who shuttled me to somebody else who eventually shuttled me back to the first person, and no one would give me information or permission to do any kind of sampling. So
Well, you're talking to the right guy.
oh,
I'm a
really? Okay.
science coordinator for the Cave Conservancy, and we're working with two researchers doing a uranium thorium analysis on speleothems right now for paleoclimatic research,
Oh,
reconstruction. Yeah,
who's doing the work?
Jeremy Shaken and McGee out of
Okay.
MIT.
Okay, cool. Good. All right. Well, they finally found the right person to talk to, apparently.
Oh,
Too
I
late
love
for
it. Yeah, I love the great connection made there, Es.
yeah.
That is great. Yeah. Yeah. Um, I was just trying to think of another question, but I like now I'm fascinated. I'm thinking about caves now too. Do you have any other research that is in the works related to climate change or anything else that Vassar is doing?
Yeah, so I've been working on two lakes on the Rensselaer Plateau, Dyken Pond and Shaver Pond, and I'm just about done with a paper about those two lakes that has, in addition to pollen and plant macrofossils, also has diatom record in it that I've been working on. And then I had my students working on Zipfelberg Bog in Rhinebeck this past year, and that's just kind of been a reconnaissance study so far, but we might take that a little bit farther eventually. And they all show similar things that have been pretty well established in the area. But one thing that I've found interesting is that the Mohonk and Minnewaska records, they are right at the dividing line between New England on the east and central and western New York on the west. And sometimes what's going on in New England is completely different from what's going on in central and western New York. And so you'll have lakes getting drying up in New England while lakes in central New York are getting filled with water and vice versa. And we seem to be on sort of a climatic divide here. And so I'm interested in whether or not I established that with the Minnewaska and Mohonk work, and now I'm trying to figure out, is that true farther north? Or is it really a divide between two different climatic regimes that are influenced by different climate processes? And it appears the answer to that is yes. So that's kind of one of my interests in there. And then also the hemlock decline is interesting because mostly people think it was probably due to a drought, but some people think it was due to an insect pathogen or some other kind of blight. And there's kind of evidence for both. And the debate has raged over the years, and everybody now is kind of back to, well, we think it's climatic, but there's obvious evidence for drought at Minnewaska and Mohonk, but there's not on the Rensselaer Plateau. We don't see that up there. So I almost wonder whether, a drought in one area sort of makes trees weak such that beetle infestations can get established, of
Mhm.
some sort, or some kind of, insect pathogenic insect kind of thing happens, and then that spreads outward and affects other areas that haven't been impacted by drought so much. So that's another kind of thing I've been kicking around thinking about.
Sure.
By looking.
Yeah, there's always multi factors into why a species is declining, or even with climate change, there's multi factors that are happening
Yeah,
to cause these things. So yeah, no, I was thinking the same thing about the drought. Like, yeah, when the climate change, it might enable more beetle infestations or other factors to come into play. So yeah,
yeah,
yeah, it's very fascinating. Even just how much of biology, chemistry, and earth science all kind of comes together when you're studying topics like this. And yeah,
yeah.
looking at pollen grains. Oh my goodness, that's a lot of time looking at pollen
Oh yeah.
grains.
A lot of time in the microscope,
Yeah.
and pollen is easy because maybe there's 30 to 40 things that you have to learn in any given sample. When you start getting into the diatoms,
Mm-hmm.
they're an utter nightmare. So uh I have about 250 different species that I've had to identify in the lake sediments from Mohonk and Minnewaska, not from Mohonk and Minnewaska, from the Rensselaer Plateau.
Mm-hmm.
And every slide is different, and no, it's really challenging.
Oh yeah. Probably dream about diatoms after a whole long stretch of looking at them, right?
Uh-huh.
It's a
Yeah, so
lot of work.
it takes me 8 to 12 years to get a paper out on these things, because that's how long it takes me to actually do the work.
Yeah,
That's
oh,
way more
yeah.
than students.
I don't doubt that. Yeah.
Yeah.
It's an awful lot of work, but we really appreciate your work and sharing your knowledge with us. And this
Well,
is
but
this is actually really fascinating work, and it really connects the history of the land to what's going on today too. So yeah, this has just been wonderful, and I thank you for your time this evening. Yeah, and if anyone has any questions, you can contact Dr. Menking, I'm sure. She'd be willing to share anything, any
yeah,
if you
here
have any
I'll
questions.
put my email into the chat so anybody
Perfect.
wants it.
Yeah. Wonderful. Yeah. Yeah. So if you have any further questions about anything, I guess, earth science related, I bet you bet you there's an answer out there for you all. And thanks everyone for your time this evening. This has been recorded, and it will be up soon on our website. And check out our other offerings that we have, everything from cultural history, a lot on mycology. We have a wonderful presenter, Bill Bakaitis, who's done many of those for us. So if you're interested in mushrooms, check that out. And we do have a whole climate change section as well with other topics on climate change. So thank you all for joining us. And thank you, Dr. Menking, for your time this evening.
Sure, thanks for having me.
Great. Thanks so much, everyone. Thank you.
Hey, bye-bye.